Hi everyone. In this video, we want to talk more about the structure that we require on the set of real numbers in order to begin to do analysis. In the last lecture, we saw that the real numbers satisfy some very important properties. They are a field. Uh, More than that, they're an ordered field, and they're also complete. They satisfy a least upper bound property, all of which are going to be important facts about the real numbers moving forward. But today we want to look at some additional structure, namely the structure of a metric space and some definitions that follow from that to learn more about the structure of the real numbers and how we will move forward with them. So first we want to start today by defining a metric space. So a metric space is a set X along with a distance function. The distance function is, and I'm realizing there's actually a typo here. The distance function is not from X, it's actually from X cross X into R. So um, it takes elements from two different elements from X and maps them to a real number. That real number is just the distance between those two values. So this should in fact say D is a function from X cross X into R. Okay. So a metric space is a set together with the distance where that distance function satisfies the following properties. The first is that the distance between two elements of your set x and y should be equal to 0 if and only if x is equal to y. So again, this is an if and only if, so it's saying if x is equal to y. So if x and y are actually the same element of your set, then the distance must be 0. And if you have two elements and you know their distance apart is 0, then they must actually be the same element. The second property the distance function needs to satisfy is a kind of reflexive property. So the distance from x to y should be equal to the distance from y to x, right? And this is an intuitive property we would expect of a distance type function, right? The distance from my house to your house is the same as the distance from your house to my house, right? And then finally, we want our distance function to satisfy a triangle inequality. So we want the distance from x to z to be less than or equal to the distance from x to y plus the distance from y to z. Again, this is called the triangle inequality because if I imagine I have a point x and I have a point z, and if I add in some third point y, essentially this is saying the distance from x to z should be less than or equal to the sum of the distance from x to y plus the distance from y to z. Okay. And so if we have a set x with such a function d, that function d is called a metric, and we call the pair, the set along with the function, the metric space. Right? So when we talk about a metric space, we're not just talking about a set, we're also talking about a way of measuring distance. This is actually not going to be super important. We often won't be very specific about this. We'll often say things like, well, the real numbers are a metric space. And what we really mean is the real numbers with the normal way of measuring distance, right? The distance from x to y is the absolute value of x minus y. We really mean that pair, the real numbers with that metric, is a metric space. It actually turns out that we it's often clear from context what metric we're talking about, and for some other certain reasons, that a lot of metrics are equivalent for the real numbers, so it actually turns out it doesn't really matter what metric you're using. However, you can also talk about infinite dimensional metric spaces, where it really does matter what metric you're talking about. It really changes the nature of the space if you change the way of measuring distance. So those are things to be careful of. Now, again, just for a few examples, so we've already talked about the real numbers and the standard sort of Euclidean distance, where we define the distance from x to y to be the absolute value of x minus y. So this forms a metric space. So if we check um, the distance from x to y is equal to 0 if and only if x is equal to y, that's true, right? The only way that the absolute value of something is 0 is if the thing inside here is 0. If x minus y is equal to 0, that means x is equal to y. Conversely, if x is equal to y, then the distance will be 0. So the first property is satisfied. It is true that the absolute value of x minus y is equal to the absolute value of y minus x. That's the second property. And the absolute value does satisfy a triangle inequality. So that we've satisfied all of the properties of a metric. So the real numbers with the standard distance are a metric space. Um, there are others. Um, so another example, let me write this in a particular way. So I'll explain what this means in a second. So this set CAB is the set of all continuous functions on the interval AB. We can define a distance between those functions by defining the distance between two functions to be the integral from a to b of the absolute value of f minus g dx. So if we do this, we can actually go through and show, although some of the details are a bit trickier, that this is in fact a metric, which satisfies, so it satisfies all three of these properties. And so this is a metric space. So you can think about metric spaces, right, as they're can be much stranger in some ways than just the set of real numbers. You can take lots of different sets and apply a metric to them. Um, you can take a finite set if you like, and you can apply very trivial metrics to that finite set. So there's lots of different metric spaces. Again, we are primarily going to be working with the set of real numbers with the standard notion of distance. But it's important to see some of this in part because we're going to define some things as we go forward in this video that work beyond just the real numbers with the standard Euclidean distance. So we want you to see that in its full generality, understand that there are some things that aren't just true about the real numbers, they're true about metric spaces in general. So we want you to really see that today. All right. Now, we're going to run through a number of different concepts related to a metric space. So these are really all going to be definitions. I'm going to spend some time walking through each of these. In fact, it sort of spills over onto the next slide. So we'll walk through all of these. But these are all things that we want to define if we have a metric space X with the metric D. Okay. So once we have a metric space, so a metric is a way of thinking about distance. So all of these things are going to, in some way, be related to thinking about points that are close to other points in an appropriate sense, sets of points that are near other points. So that these are all going to encapsulate some notion of closeness in a way. So the first thing we want to define is we want to define a neighborhood of a point. So a neighborhood of a point X, which we write as n sub r of X, it's the set of all points Y such that the distance between X and Y is less than R for some R greater than 0. So if you want to think of this visually, you have some point X. This R is called R because if you're in like the plane or in on the real number line, this is literally like a radius, right? So this would be the set of all points that are within distance R. of X. So let me actually, so there's X. So the neighborhood in is the set in blue here, right? This is n sub r of X. It's the set of all the points that are within distance r of that point X. A deleted neighborhood is just that neighborhood, but take out the point X, right? So the deleted neighborhood are all the points in the neighborhood that aren't X. That's sometimes just a helpful way to refer. If we want to sort of exclude X and just talk about the points near X, we can talk about the deleted neighborhood of X. So, uh, in a lot of ways, you should think of neighborhood like you think of the plain English, the mathematical word neighborhood, in the same way you think about the plain English word neighborhood, right? And there's some radius, right? So you may sometimes talk about your neighborhood and mean, the block of houses that you live on. You may at other times talk about a neighborhood as being, say a subdivision that you live inside of. You may at other times talk about a neighborhood as being something like West Charlotte, right, or an even larger subset. So neighborhoods come in various sizes, but they're subsets of things that are close to some point X. So that's the idea of a neighborhood. Now, the reason we want to define a neighborhood really is because we want to be able to define things called interior points. So a point X is an interior point of a set E if there is some neighborhood in sub R of X that is a subset of E. Okay, so let's clear our picture here and look at this. So imagine I have some set E. So here in blue, let's say this whole thing is my set E. And I have some point sitting inside here, X. And I want to know, is X an interior point? Well, in this case, X is an interior point because I can construct a neighborhood around X where I can find some radius so that this entire neighborhood that I've constructed, this entire neighborhood lives inside E. Okay. So point X is an interior point of a set if there's a neighborhood that lives entirely inside the set E. Now notice it doesn't say that every neighborhood lives entirely inside E, right? That certainly wouldn't be true, right? If I took my radius really, really large, right, I could have, a neighborhood that looks like this. And certainly if I did that, that neighborhood doesn't live entirely inside E. But it only says here that there is a neighborhood. There exists at least one neighborhood for some r greater than 0, such that that neighborhood lives entirely inside E. Now, as I've drawn this, you may be looking at it and going, well, of course, okay, that seems like every point that would work. And in fact, as I've drawn it here, that's true, it would work. But let's look at a slightly different example. And let's maybe just think of an example in R. So imagine I had the closed interval, say 1 to 3. Now, if I pick some point, if I pick the point, say, 2, sitting inside here. So my set E, just to be clear here, so my set E is this closed interval. It's this whole set. So I'm imagining E is the closed interval 1, 3. My point X that I'm looking at, trying to decide if it's an interior point. If I look at 2, then if I take the neighborhood of, say, radius 1/2, then here the neighborhood of radius, or sorry, of radius 1/2 of 2 would just be the open interval 1.5 to 2.5. And clearly, the neighborhood of radius 1/2 centered at 2 is a subset of E, which is 1, 3. So 2 is in fact an interior point. Okay, but what if we go back and change the point that we're looking at? So what if I come up here and instead of looking at x, I'm going to look at a different point. Oops. So let me instead, I'm sorry, I messed up my picture a bit here. I'll have to go back and fix it. All right, so okay, some trouble here. All right. So now if I go back to my line, I'm still looking at the interval. Boy, that's a real mess. Let's just clear that. All right, let's redraw this. We go back, we have the interval 1 to 3. This is our set E. Close interval 1, 3. And now I'm going to pick X to be the point 1. Okay. So there's my X value. Okay. Now notice here that no matter what radius I choose, right, even if I choose this radius really, really small, there are going to be points in the neighborhood of radius R that are not in the interval 1, 3. Okay. So for any R greater than 0, for example, 1 minus R over 2 is an element of the neighborhood of radius R around 1. So what I'm saying here is if you go down, this would be 1 minus R, this would be 1 plus R for any R. And if I go down here, there's some point inside of here, 1 minus R over 2, that's in the neighborhood of radius R around 1, but 1 minus R over 2 is not in my set E, right? It's not my set E because it's strictly less than 1. So what does that tell me? That tells me that the neighborhood of radius R centered at 1 is not a subset of E for any value of R. And hence, X is not an interior point. Okay. So we have to, and it sort of makes sense, right? If you look at this interval, that point is not in the what you would probably consider the interior, right? So what we're doing here is rigorously defining what do we mean by interior. And now we have a definition that lets us say this is exactly what we mean by something being an interior point. All right. 3 and 4 are fairly, they're just definitions. So if we take a set E and we take all of its interior points, then we call that the interior of E, right? So for example, in this set, the interior of E would be the open interval 1, 3. Um, Number 4 is E. E is called open if every point of E is an interior point. So again, like we often might talk about, you might probably heard the terminology like the open interval AB, meaning this. It is that interval is open. Every point of that interval AB is an interior point. But by definition, if you're looking at a set and trying to figure out is it open, the question you need to ask yourself is every point an interior point? If it is, then it's open. If it has any point that's not an interior point, then it's not open. So the last two are really just sort of just terminology more so than any big conceptual definition. Right. Now, the next piece, number five, talks about something called an accumulation point. And accumulation points are actually going to be really important when we want to start rigorously defining limits, because accumulation points are really going to tell us about the types of points where we can think about taking a limit. So, a point X is an accumulation point, or also called sometimes a limit point of E, if every neighborhood in sub R of X contains a point of E that is different from X. Said another way, for any R, you want to make sure that the deleted neighborhood of radius R around X intersected with the set E is non-empty. All right. So let's look at an example here. So let's think about the set, say, of numbers of the form 1 over n, such that n is equal to 1, 2, 3, so on and so on. Okay. If I look at this set of numbers, um, I can sort of probably have some sense that right they're approaching zero. So what I'm actually going to show is that zero is an accumulation point of this set. Now, the first thing I want to point out here, right, zero is not in this set. A point need not be in a set to be an accumulation point or a limit point of that set. It can be, but it doesn't have to be. Okay. So in this case, I'm going to show that zero is a limit point. Zero is a limit point of, let's call this set A. Okay. So what do I want to show? I want to show that if I look at any neighborhood, so what is n sub r star of zero? So that is the set from minus r up to zero, not including zero, union zero to r. These are all the points within distance r of zero, not including zero. Now, I want to show that there's always an element of my set A that intersects this set n sub r star of zero. Okay, so how do I do that? Well, by the Archimedean order property, and it's not actually the one we stated, but it's the one that, there's a list of equivalent ones. So by the Archimedean order property, there exists some capital N, a natural number, such that 1 over n is between 0 and r, right? So one of the equivalent versions of the Archimedean order property says that for every real number x, there's a natural number n such that 1 over n is less than x. So here my x is like r, and I'm just finding a number 1 over capital N. Okay. So what does that mean? So 1 over n, well, n's a natural number, so 1 over n is in A, since n is a natural number, and 1 over n is also in the deleted neighborhood of radius r. I'm sorry, the deleted neighborhood of radius r around 0, since it's between 0 and r. Okay. And right, we've done this for an arbitrary r. So n sub r star of 0 intersect A is not the empty set for every r. I can do this for every r greater than 0. So hence, 0 is an accumulation point or a limit point of the set A. Even though 0 is not in there, it's still an accumulation point of that set. Okay. So accumulation points of a set are, I guess the best way to think of them is they're all the things that could be limits of sequences of things in the set, right? Which is where the limit point terminology comes from. If you sort of graphically looked at this, right, you would see that, okay, here's 0. It's not in my set. There's 1. So if I sort of plot my set, right, things are sort of clumping up at 0. Right? You would start to notice like things really seem to be, you know, and I can't possibly graph all those, right? But you sort of really start to notice that even though 0 is not in the set, things are really sort of clumping up at 0. And that's what this notion of accumulation point is. Another way of sort of thinking about it is there are points as close as you would like to 0 in your set A. So you can find a point that's as close as you would like to 0, even though 0 isn't actually in your set. All right. The next couple are again just sort of terminology. So number 6, E is closed if every point of E is an accumulation point of E. So if every point of a set is an accumulation point of that set, then the set is closed. The closure of a set E. So if I have a set E and I want to talk about its closure, it's the set E and all of its accumulation points taken together. So it's the union of E and the set of all accumulation points of E. So you just take E and you add in all of its accumulation points. And then finally, we call a point isolated. A point X in a set E is called an isolated point if X is not an accumulation point of E. So if you have a point in a set, but that's not an accumulation point of that set, then it's called an isolated point. Again, when you see these things, often, in a lot of examples, I don't want to say they're obvious, but, if you take the set, for example, let's put 1, 2, and 3 on the number line here. Let's say you take the interval from 2 to 3, including 2 and 3, and you union with it the singleton 1. So let's say you take your set E is going to be the single point 1 union with the closed interval from 2 to 3. Okay. Maybe it's not surprising that the point 1 is an isolated point. Okay, why is it an isolated point? Well, it's not an accumulation point. Why is it not an accumulation point? Well, take the, say, neighborhood of radius 1/2. The deleted interval does not intersect the set A, or sorry, the set E anywhere, right? The only place this whole neighborhood intersects is at the actual point. But again, the definition of accumulation point says you need it to intersect at a point different from 1, right? So the point 1 in that case is an isolated point of the set E. All right. These are a lot of definitions, and there are a lot of things that are then going to follow from these. Some of them are fairly technical. They're going to test your proofwriting skills a bit, and that's something that we will work on together. Okay, so as you're trying on the next homework assignment to prove things related to limit points and open sets and interior points and isolated points, come and ask for help. Set up an office hours appointment. Come talk to me, because this stuff can be quite challenging. All right. Now, after all those definitions, of course, we define things and then we start to look at the different ways in which they're related. Okay. So if I have a metric space X with metric D, then all of the following 6 things are all true things. So Every neighborhood is open. So a neighborhood of a point is always an open set. Number two, every neighborhood of a limit point of E contains infinitely many points of E. Number three, a finite set only has isolated points. Number four, a set is open if and only if its complement is closed. Number five, the interior of a set is an open set. And number six, the closure of a set is a closed set. Now, some of these are not like some of these are almost the proof is almost trivial. So if you take the interior of a set, so you take a set, you take all its interior points, that's the interior of a set. Well, of course it's open because an open set is a set where every point is an interior point, and you just created that interior of a set by only taking the interior points. So of course it's an open set. The same with the closure of a set. The closure of a set is the set unioned with all of its accumulation points. And a closed set is a set that contains all of its accumulation points. Well, in constructing the closure of the set, you added in all the accumulation points. So of course they're there, and of course it's a closed set. So five and six are really just looking at the definition in a very straightforward way. The other four, however, take some work. We're not going to prove all of them, but let's sort of at least sketch out the ideas of a couple. Um, so let's say I wanted to prove first that every neighborhood was open. So the fundamental idea here is, so imagine I have some point X and I have a neighborhood of radius R around this point X. Okay. And now I want to show that this is an open set. Well, what does that mean? That means I need to show, if I want to show a set is open, I need to show that every point is an interior point. All right, well, let me just come over here and grab an arbitrary point in this set. So let me just grab a point here. I'm going to call it Y. I'm going to show that Y, this arbitrary point I've chosen, is an interior point. And if I can do that for an arbitrary point Y, then that means I could have done it for any point in the set. And so it must be that every point is an interior point. All right. Now, what's a little tricky here is I've got to figure out, I want this to be an interior point. So I need to put a neighborhood around Y that stays totally inside of this set n sub r of x. Okay, and the really the tricky part here is figuring out what's the radius of that set that will make sure I stay that will make sure essentially my green circle stays inside of my red circle. And the trick here is you basically imagine that you drew a straight line through here. Okay, so this distance here. This is the distance from X to Y, whatever that happens to be. And so the remainder of this, piece here in blue, this is R minus the distance from X to Y. Okay. So for this green set, I want to make sure I stay sort of totally inside here. I could actually just use R minus D of XY, but if I want to like really make sure that 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 I don't run into anything, I could make the radius of this green circle half of that distance, so that I don't come anywhere close to the boundary of the red set. Um, so if I choose, say, S to be R minus D of XY over 2, then the neighborhood of radius S around Y would be a subset of the neighborhood of radius R around X. And I can do this for any point Y in my set. Therefore, every point of my neighborhood must be an interior point. Therefore, my neighborhood is an open set. The other one I'll sort of quickly sketch out because I think it illustrates, a common something that's sort of special about finite sets. So we'll look at number three. A finite set has only isolated points. So if we have some finite set, the idea here is so let's let A be a finite set. And in that case, I could just, A1, A2, up to however many elements it has, AN. Okay, there's only finitely many. I can write down a list that has them all, right? So I have my finite set, and choose AI. So we're going to choose an arbitrary thing in my set A. I want to show that this is an interior point. If this, or sorry, show that this is an isolated point. If this is an isolated point, then since I chose it arbitrarily, every point must be an isolated point. Um, so I'm going to choose AI and calculate R be 1/2 times the minimum over all n not equal to I of an minus AI. So let me explain what I'm doing here. Or sorry, it's not right. That would work if we're talking about the real numbers, but I want here distance an AI. Okay. So the idea here is I'm going to look at the distance between AI and every other thing in the set. Okay. And I'm going to find the closest other thing in the set. Now, because there are only finitely many things, they all have to have some, they're distinct, so they have to have some positive distance. It has to have some minimum, which is also a positive value. I'm then going to take half of that. Okay. Well, then if I look at the neighborhood of radius r around a sub I and intersect it with A, that's going to be the empty set. Okay. Sorry, if I take the deleted neighborhood of A sub I and intersect it with A, that's going to be the empty set, right? Because everything else, the distance from A sub n to A sub I is greater than R for all n not equal to I, right? But every other point is greater than distance R away. So I have constructed a neighborhood now that does not intersect A in any point other than AI, which is the place where it's centered. Therefore, AI is an isolated point. I could do this for any point AI in my set. I just go to that point, I look at the distance to all the other points, and then I find the smallest distance, cut that in half, and then I construct the neighborhood of that radius around there so that I don't have to worry about that neighborhood intersecting anything other than the point where it's centered. Okay. So finite sets can only have isolated points. If you're going to have any sort of accumulation point, that requires that you must have infinitely many points. There's no way to do that otherwise. Okay. The other proofs again work through similar sorts of ideas. You'll explore some of those more in some of the exercises coming up, but we will stop sort of proving with those. All right. Finally, we come to some facts about unions and intersections. Um, so we often want to build open sets or closed sets out of other open sets or closed sets. So if we take a bunch of open sets and union or intersect them together, we might want to know, well, will the resulting set still be open or still be closed, right? And the answer is, well, it depends a little bit. So if you look at the first two here, this says so the number one says for any collection of open sets, the union of those open sets is open. So this could be a finite collection of open sets. It could be an infinite collection of open sets. The union of open sets is always open. Now, if you look at the second one, it looks very similar, but there's a slight difference. For any collection of closed sets, F sub alpha, the intersection of those closed sets is closed. So again, no specification here. Could be an infinite collection, could be a finite collection, but any collection of open sets, if you intersect them all together, the intersection is closed. Now, of course, looking at those two, it begs the question, what happens to an intersection of open sets and what happens to a union of closed sets? Well, it turns out we can get similar results there, but now we need to restrict ourselves to finite collections. So number three says for any finite collection of open sets, the finite intersection is open. For any finite collection of closed sets, the finite union is closed. So again, the way to sort of think of this is open sets work really well with unions, closed sets work really well with intersections, right? One and two basically says, that'll be fine. You can build other open sets out of open sets by unioning, other closed sets out of closed sets by intersecting. Um, if you want to do the opposite, though, if you want to use intersections with open sets or unions with closed sets, you probably need to make sure you're only working with a finite collection. Either that, or you just need to be careful. It's not something that's automatically true. It is possible that you could have some infinite collection of closed sets that unions to a closed set. So this isn't saying it's never possible, but it's saying in general you can't assume that that's going to happen. Okay. Now to just sort of get the flavor of one of these proofs, if we look at the first one, so if we wanted to prove that a collection of for any collection of open sets, the union is open. Uh, so what do I want to do? I want to show that the union is open. So I'm going to let X be something in the union of all of these O sub alphas. Okay. Now, what do I want to do? If I want to show this set is open, I take something in that set, an arbitrary thing in that set, and I show that it's an interior point. Okay. Now, since X is in the union, it's in at least one of these O sub alphas, right? I don't know which one, but it's in one of them since it's in the union of all of them. So then X is in, let's call the one that it's in, say, O sub I for some I, right? I don't know what value it is, but there's some I where X is in a particular one of these things that makes up the union. Okay. But that thing is open. Okay. So since OI is open, X has to be an interior point of OI, and hence there is some radius such that the neighborhood of radius R around X is contained entirely within O sub I. Okay, but if the neighborhood of radius R around X is contained entirely within O sub I, then it's also contained entirely within the union of all the O sub alphas, right? The union of all the O sub alphas are all of the things that are in any one of the O sub alphas, right? And O sub I is one of them. Okay. So since this neighborhood is in this particular one, this is the collection of all of those things sort of glued together. So this must be in the union as well. Okay, well, so then what do we have? So X is an interior point. union of O sub alpha. Since it was arbitrary, since it was chosen arbitrarily, all x in the union of O sub alpha must be interior points. And hence, since every point in that set is an interior point, the union of the O sub alphas is open. Yeah. A similar idea works for closed sets, although there's also sort of clever ways of doing that using complements, and sort of same thing for three and four. So again, these are the sort of things you just want to drill down on these definitions, carefully write out what each step means, and typically you'll end up with a correct proof. I'm not saying that's easy, right? But it's sort of what we often call definition chasing. So if we're very careful about our definitions and just sort of step through piece by piece in each part of the definition, we will often end up with a correct proof. That concludes what we want to talk about in this video. So, to sort of recap, right, we defined metric spaces, we looked at some definitions related to metric spaces, and then we've looked at a few theorems about neighborhoods, about open sets, about closed sets, about isolated points and accumulation points here at the end. Now, broadly speaking, this is really dealing with something that is really about the topology of metric spaces. If that word doesn't mean anything to you, that's okay. We sometimes offer topology as an elective, so you may have an opportunity to take that at some point. Um, but if you have taken a topology course, you may be quite familiar with some of these notions. Metric spaces are very special kinds of topological spaces. So, not in topology, lots of very weird things can happen with sets. Metric spaces are very nicely structured topological spaces, and so sort of nicer things tend to happen because you have more structure. Um, so if you've taken topology before, sort of you might have a little leg up in some of these proofs, but also know that metric spaces are nicer than just general topological spaces. Metric spaces, for example, are Hausdorff. Again, if none of this means anything to you, don't worry about it. But if it does, metric spaces are Hausdorff. So you don't have to worry about weird separation axioms failing and things like you might with just again a general topological space. Um, Now what we've done is we have built up over the past two lectures the structure on R, which is going to allow us to start rigorously defining limits. We need things like accumulation points and open sets and closed sets and all of this. We need all of this in order and a metric to make sense of what a limit ought to be for a function, even just a function from R to R. To do it in the most general setting, we need all of these notions. And we will begin next time then with using those notions to rigorously build the definition of the limit.